The equations of classical mechanics, which describes how a system changes over time, breaks down in a quantum world. A different mathematical approach is needed to describe how a quantum system evolves. Austrian physicist Erwin Schrödinger provided the solution to this problem in 1926 with what is now called the Schrödinger equation. This equation actually describes the changes in what is known as the wave function of a quantum system. The wave function captures all information needed to describe a quantum system fully. The Schrödinger equation describes how the probability of locating a particle or a system of particles evolve in a wave-like manner, and so provides some insight into wave-particle duality, the property of particles to behave like waves and waves behave like particles. Mathematically, the Schrödinger equation is based upon algebra and calculus. Quantum mechanics can also be described using the mathematics of matrices, which I will cover eventually. Both approaches are equivalent. The Schrödinger equation was a significant advance on the mathematics of classical physics and provided a foundation that was built upon by English physicist Paul Dirac and helped to create quantum electrodynamics, or QED, a key plank in modern physics.